Hello guys, in this video we are going to be discussing the problem maximum sum of subsequence with non-adjacent elements. This was there in the Leetcode weekly contest that appeared last week. So in the problem they have given us a nums array in the beginning. So they have given us a array of nums. So suppose the elements of the nums array are A0, A1, A2, A3 till An minus 1. What we have to find is a subsequence such that the sum of the elements in the subsequence is the maximum, and the subsequence should be such that inside that subsequence no two elements should be adjacent in the original array. So we can take A0, we can take A0, A2, but we can't take A0 and A1 in a subsequence because they are adjacent to each other. We can't take elements which are adjacent to each other in the subsequence. So we have to find the maximum sum subsequence. Actually, this part can be solved using a simple DP or O of n approach, but they have complicated the problem and they have given us some queries as well. Inside each query, so there are some queries. For each query there is one index and there is some value associated with that particular index. So they are asking us to apply this change to this particular array and find the maximum subsequence. So we have to apply this. How to apply this? We have to change the value of the first index. So here the first index value will be A1. We have to change the value of A1 to minus 2. After applying this, we have to find the maximum sum subsequence. Okay, we don't need to find the maximum sum subsequence, we just need to find the maximum sum. Okay, and there will be some number of queries. So we have to find the sum after the maximum sum after each of the queries, and what we have to output is the sum of the maximum sums of each of the queries. So suppose the sum of this particular the maximum sum of this particular query is S1 and the sum of the second query is S2, and till there are suppose there are m queries. These are the values of the maximum sum of each of the queries. So we have to output S1 plus S2 plus till Sm. So this is the value that we have to output. So what we can do? So applying DP after making this change every time would result in it. So for applying DP one time, the time complexity would be O of n, where n is the size of the array. Where n is the size of the array. Applying O of n after each query would be O of n into q, where q is the number of queries. So that's a large value according to the constraints given here, so we can't do that. So what we have to do is we have to find a more optimized approach. The optimized approach for this particular problem, one of the optimized approach, actually there is a DP solution as well. It's actually more complicated. A DP solution that doesn't require O of n into q, it's a complicated solution. What I'm going to be discussing is a segmentary solution. When you hear the word segmentary, you may think it's complicated, but this solution is not that much complicated. It's just a simple modification on the basic segmentary. So suppose they have given us an array 1 0 1 2 3 4 5. I just took a simple array 0 1 2 3 4 5. So what do we do in a segment tree? First we split this array into two arrays, right? So in the first array the values would be till the middle element, so it will be till the values will be 0 1 2, and in the second subarray the values will be from 3 4 5, and this will go on, so this will again get splitted. This will become 0 1, this will become 2, this will become 3 4, this will become 5, then this will get splitted again 0 1 3 4. Since here only one element is there, we are not splitting it again. We are splitting it on the basis of the middle element, so we are splitting till the middle element. So what we are going to do is that, so the problem with the DP approach is because of the number of queries, right? So since the number of queries are very can be large, applying this O of n approach, applying this O of n after every DP will be of very huge time complexity. But for the segmentary approach, what is the difference is that, suppose like in a query they are asking us to change the value of the first element, for example. So they have asked us to change the value of this particular element. To change the value of this particular element, if we apply the change on this particular element, it will only affect 1 2 3 4. It will only affect 4 values. But if it would have been if it would have been the DP approach, we should have had applied the change on the entire array. Now you may think like that here if we use the DP approach, 6 elements would be affected, but if you use the segmentary approach, also 4 elements are getting affected. The difference is not that prominent, but it's because it's a small array. If it's a large array, the difference would be much more prominent, and the number of elements in a segmentary approach that's gonna get affected for each update operation is log n. Actually we have to take the seal of log n. What's n over here? N is 6, because 6 elements are here inside this particular array. 6 elements are here, so we have to take seal of log 6. What is log 6? Log 6 is something 2 point something, right? 2 point something. If we take the seal of that, we will get 3. Okay, so 3 elements should be affected. Okay, when we did it here, I said 4 elements are getting affected, but like we don't need to consider this element, because like it's the last element, and like we are not applying any operation on this. Like we are returning from this particular element, so we can consider it as 3 element, or we can consider it as log n plus 1 element. So it doesn't make much difference. So generally when we are speaking, the number of elements that's going to be affected is log n elements, and log n will be much less than n. So for each update operation, for suppose there are q queries, for each query we are only affecting log n terms. We are only applying log n operation. This is much smaller than the q into n time complexity earlier. So that's why we are using a segmentary approach. And how does this segmentary approach work? for this particular question, how the segmentary approach will work is that for every suppose okay, this is a node, 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 this is a node. Okay, all these in a squares are nodes. So for each node we have the option to so we will be choosing elements on the leftmost side and on the rightmost side. So on a particular node we will be only dealing with selecting the leftmost element and the rightmost element. The elements in between the leftmost element and the rightmost element would be handled by the recursive calls. So we will be only dealing with the leftmost element and the rightmost element. So we have the option to either choose this leftmost element or not choose this leftmost element, or either choose this rightmost element or not choose this rightmost element. Our decision here would affect the future decisions, because if we are choosing this leftmost element, we will not be able to choose the element after the leftmost element. If we choose this rightmost element, we will not be able to choose the element after the rightmost element. So our decisions here would affect the further decisions as well. What we are going to do is that we will apply all the such possibilities. We will apply a possibility. So suppose 1 is for picking and 0 is for not picking. Here what all possibilities are there? We can apply 1 1. 1 1 means we are picking the leftmost element and picking the rightmost element. We can also apply 0 1. We are not picking the leftmost element and we are picking the rightmost element. 1 0. We are picking the leftmost element and we are not picking the rightmost element. 0 0. We are not picking neither the leftmost element or the rightmost element. So these are the possibilities that we have. And for each of these possibilities, how will we compute the values for each of these possibilities? The values for each of these possibilities will be computed like this. So for if we are, so suppose the possibilities that I chose is I and j as a general. So suppose I can be anything 0 or 1 and j can be 0 or 1. So what all possibilities can this choose? The possibilities that this node can choose will be either I0 or I1, because we already chose I was passed on from this parent node. I was passed down from this particular parent node. So I is fixed. I is whether we are choosing the leftmost element or not choosing the leftmost element. So I can either be 1 or 0. Since we are not sure, we have put a variable I. Now the only option for this particular node is whether to choose this rightmost element or not. Since we haven't applied any operation on 2 over here, we have the option to choose this particular rightmost element or not. So we have the option to either not choose or choose. And what are the options associated with this node? The options associated with this node are 0j and 1j. Since the decision for this node is this element is already made in the parent node, and that is j, so we can't change that. But what we can change in this particular node is whether to choose 0 or whether to choose 0, or whether not to choose 0 or whether to choose 0. So that is the decision associated with this particular node. And how will we find the optimal answer for this particular node? So the optimal answer for this particular node will be based on the answers of its two children nodes, right? So the optimal answer for this node can be decided according to this. So optimal so answer of I, j will be equal to maximum of ants of I. This ants I is for the child node. Okay, wait, I will write parent instead of child. The answer for parent for its particular choice of I and j. So parent chose a particular I and j, right? So the answer for parent's choice of I and j will be equal to child I0 plus child. Okay, sorry. Oh, wait. I will write this again. Is it visible? Write with another pen. Parent I j will be equal to. So the parent I j can be affected by these possibilities. Left child I0. If the left child doesn't choose the rightmost element, if the left child doesn't choose the rightmost element, the right child can choose the leftmost element. Okay, why is this? If the left child chooses the rightmost element, if it was 1 here instead of 0 over here, if it was 1, we couldn't have done this, because if the left child chooses the rightmost element and put a 1 over here, and the right child also chooses the leftmost element and put a 1 over here, then 2 adjacent elements would be chosen. So we can't do that. So since the left child didn't choose the rightmost element, the right child can choose the leftmost element. So here. So if the left child had chosen 2 over here, the right child can't choose 3, because then 2 adjacent elements will be chosen. But since if the left child don't choose 2, the right child have the option to either choose 3 or not choose 3. So there is no condition against leaving 2 adjacent nodes not chosen, right? So we can either leave these 2 nodes as unchosen, or we have the option to choose any one of these, but not both of them. So that's what we are writing the conditions over here. So since the left child didn't choose the rightmost element, the right child can choose the leftmost element. And what all conditions are there else? So if the left child didn't choose the rightmost element, the right child also has another option to not choose the leftmost element. So when I am saying the leftmost element of right child, I am implying this 3, and when I am saying the rightmost element of left child, I am implying this 2. I think that wasn't clear previously. So when I am saying the rightmost element of the left child, I am implying this 2, and when I am saying the leftmost element of the right child, I am implying this particular 3. So they can leave both the adjacent elements, not chosen. And there is another possibility as well. Another possibility is the left child can choose the rightmost element, and then the right child has the option to not choose it, because if the right child also chooses the leftmost element as well, then 2 adjacent elements would be chosen, and that's against our original problem statement. So these are the possibilities for parent ij. We have to choose the maximum of these possibilities, and this will be stored in parent of ij, and we have to recursively do this for every node. How will we find this particular value? This particular value will be recursively obtained from its children. how will we find this particular value? This value will be recursively obtained from its children. And what is the base condition? The base condition would be the node with one child on it. So this is the base condition. And what will happen in this particular base condition? In this particular base condition, suppose we name this as base. There can be four possibilities, right, for this base condition: base of 1 1, base of 1 0, base of 0 1, base of 0 0. These are the four possibilities. In base of 1 1, we equate this as the value of this particular node value. But for base 1 0, 0 1 and 0 0, we equate this as a very less value, like negative infinity, or we can leave it as 0 itself. Either we can put negative infinity or we can put 0, because when we put 0, it's like we are not choosing this value, right? We are not considering this value, so we can leave it as 0, so its effect is not affected. So for these three conditions, since like why are we putting 0 for 1 0? Since only one element is there, but for the leftmost element and the rightmost element for one is 1 itself, but it's giving two different conditions. It's asking us to pick the leftmost element, which is 1, and they're also asking us to not pick the rightmost element, which is 1 also. So they're giving us two contradicting commands, so we are leaving it as 0. And for base 0 0, they are clearly specifying us to not take it, so we are leaving it as 0. So only for the base 1 1 condition, we are giving it the value of that particular node. So this is how we compute the segmentary. So, and for the update condition, we can just change the value of this particular node, and we can apply the segmentary point update operation. So we just have to, we just have to, from this particular node we have to go over here, and we from this particular node we have to go over here, and from this particular node we have to go over here, and the value is updated over here. The updated value will affect this node. So this node will compute the value. It already has this particular value, and it has the updated value of this, so it will choose the optimal one, and it will return the optimal answer here. And this particular node has the answer returned from this, and also already has the answer from this, and it will choose the optimal answer, and it will choose the optimal answer, and it will return the optimal answer to this particular node. So this particular node has the returned answer from here, and it also has the already computed answer of this particular node, and it will choose the optimal answer of both the nodes, and it will choose the optimal answer, and it will store the optimal answer over here. So that's basically the problem, and I will show you the code for this problem right now. Hello guys, the code for this particular problem is as okay, I will show you the code for this particular problem. Not able to zoom it. So I will show you the main function first. This is the main function. We are building the segmentary first. I will show you the code for building the segmentary, and then I am iterating through the queries. And after iterating through the queries, the position to update is stored in the first index, and the position of the value is stored in the second index. And after updation, so I am calling the function to update the segmentary. After updation, I am finding the maximum element from these conditions. So this is a segmentary will store the values for each of the nodes, and what these parameters mean is that this parameter means the first node. So first node is the root node. So we are only considering the root node, and for the root node, I am checking the condition where we not pick the leftmost child and where we not pick the rightmost child. And here for the root node, I am considering the value for picking the leftmost child and not picking the rightmost child. And here for the root node, I am checking the condition, the checking the value for picking not picking the leftmost child and picking the rightmost child. And for the root node, I am checking the condition where I pick the leftmost child and I pick the rightmost child. So I take the maximum values of this and I take the modulo. You have to take modulo 10 raised to 10 raised to 9 plus 7. And if it's less than, less than 0, I'm making it 0, and I'm returning. So this max will be the answer for this particular query. I am storing the answer, this max. I am incrementing this max to this variable ans, and I am returning ans at the end. And I will show you the build and the update function for the segment tree. The build function for the segment tree. So this is a segment tree. I have given a large value for the number of nodes. So this represents the number of nodes. Okay, you can, I just gave a random value. Okay, you can, calculate how many nodes will be there. So usually the number of nodes will be equal to 4 4 into n plus 4 into n plus 1 in a tree. So this is the number of nodes in the array that they give us, but in the tree, the number of nodes will be around this value. So you can, check the value of n from the test case, and you can assign this particular value. And here I'm giving 2 because here it can be either of the two values, either pick which is 1 or not pick which is 0. So two values are possible over here, and two values are possible here as well. So in the build function, when we reach the base condition, I have told you the base condition already, right? The base condition is the condition where only one element is present in a node. So only when only one element is present in a node, we take the uh, for the case where uh, where we have to pick the leftmost value and pick the rightmost value. For that, for only that condition, we take the value of nums of L, where nums of L is the single value present in that particular node. And I'm taking the max 0. So if it's a negative value, I am taking it as 0, because if we take it as 0, the value won't get affected. I don't want to take it as negative. That's why I'm taking max. And for all the other values, I am putting it as 0. And I'm splitting the build function. I'm splitting the build function from L till mid, and from mid plus 1 till R. Initially L is equal to 0 and R is equal to n minus 1, the size of the nums array. And what we are doing here is that for each case, so segmentary of I means the that particular node. For that particular node, if we want to compute the value, we have to consider the left child, which is segmentary I into 2, and the right child, which is segmentary I into 2 plus 1. So this is the p for that particular node. uh, P can be either 0 and 1, and Q can be either 0 and 1. So I didn't want to write it out, so I wrote a for loop. So P can either be 0 and 1, and Q can either be 0 and 1. So for each of the P and Q cases, there are three conditions. I have already told you the three conditions when I wrote it in paper. So this is the left child. If you are not picking the rightmost element of the left child, we have two possibilities. We can not pick the leftmost element of the right child, or we can pick the leftmost element of the right child. So this is the case for not picking the rightmost child of the rightmost element of the left child. And if we are picking the rightmost element of the left child, our only option is to not pick the leftmost element of the right child. So I am storing the max, and yeah, that's basically it. For that's basically the build function. Now in the update function, so we have a position. This is the position that we want to update, and we want to update it with the value val. Now in this case, we are checking whether we are going in the right direction. If we are like, if our position is not in the range that we are currently considering, then the range that we are considering is not correct. So we are going in a wrong sequence of wrong branch. So we want to backtrack. We want to find the correct branch. If we have located the correct position, so if it's L is equal to R, if we are currently at the desired position, hmm, I am not checking whether L is equal to R is equal to the position that we want to reach, because it's like uh, almost guaranteed, because we are backtracking when we are in the wrong branch, in the wrong node. So we are guaranteed that when we reach a node with a single value, it will be in the node with the value uh, which has the position pos. Okay, and we are updating the value, updating the segmentary one I11 with the new value, and we are doing the same. We are splitting the array, we are splitting the update function into two, and we are doing the same for loop operation over here as well. Yeah, that's basically the code. Actually, it's a simple code. Just had to come up with the segmentary, and which element to choose, which element not to choose, and you had to think a bit. I also didn't get this approach in contest. I got this approach only after thinking a bit. I was mainly stuck with the DP approach for a while. I was trying to do the DP, some complicated approach, but I was not able to implement it. Then I did this segmentary approach. Okay, yeah, that's basically the solution. If you found the solution helpful, please comment down below, like where how I can improve in the future, and please like as well if you found the solution helpful. Like if you didn't find this solution helpful, can you comment down below whether which part you didn't find helpful, so I can improve in the future. Thank you.